Okay, hello everyone. Welcome to our webinar series titled Introduction to Photonics Packaging. My name is Mark Rensing and I'm joined by my colleague Camille Gradkowski. So in our first webinar last week, we provided an introduction to photonics packaging and covered some package design considerations. And in today's webinar, we'll discuss electrical packaging and thermal management. So today's webinar will last about 40 minutes and we've allocated about 15 minutes at the end for a Q&A. So please feel free to ask any questions you have in the chat or Q&A buttons. Without further ado, I'll hand over to Camille to begin the presentation.
Okay. Good afternoon, everybody. Yes, so today we're discussing two topics before we go to the clue of the course, which is the optical packaging part. So today, electrical packaging and thermal management are kind of related because you will have the thermal management when you're dealing with electrical packaging by the nature of things. So it's good that they're kind of co-joined in this talk. So looking at electrical packaging, what we have to do is essentially look at the legacy, where we come from, because microelectronics has been on the rise ever since we had the first transistor in the 1940s. So I've pulled up some examples of just electronic packages from the web. For example, this i486 processor by Intel from 1989. You can see the die design on the left. It's pretty sophisticated, even though the processing node was of the order of several hundred microns. But what's more important from the packaging perspective is that you can see the die itself as it is installed into the package, and the bond pads are wire bonded across to the package. And note that all the wire bonds and all the bond pads are positioned on the outer edge of the package, of the chip. And then this package is then integrated into a larger mechanical package, which translates these pins that go out from the PIC onto the pin grid array. So this is how the processors looked like back in 1980s, back in 1990s. Now we have much more sophisticated processors with much greater levels of integration. This is another processor by Intel that I could find a neat schematic of. So the die design is much more complicated. And you can see that the processor is integrated by flip chip this time into a multi-layer PCB with vias. So this is much more complicated, much more advanced. So the idea with electronic packaging that we deal with when we're talking about photonics packaging is that we want to, as much as possible, utilize these advancements and not to reinvent the wheel. However, what we were observing over the past couple of years, and not only perhaps in photonics packaging, but it's becoming more evident in photonics packaging, that the companies are moving away from uniform designs, as you can see over here, and moving toward the chiplet model where different functionalities are split between different dies, which can use different manufacturing nodes, and therefore are then commonly integrated onto a single carrier substrate. And I'll show some examples of that later. So if you compare that to the electronics, the photonics package designs, you can immediately see that they're much more let's say less complex and complicated. This is a package that we made back in 2018, 2019, that sort of scale. So this is much less sophisticated than what you saw before. At the center, of course, we have the photonic integrated circuit, which is coupled optically with a fiber. And then the electronic side is the connectivity is established using two PCBs. So we have north and south PCB, which serve both as a DC connector and as an RF connectors. So the purpose of essentially the purpose of electronic packaging is to ensure the electrical interfacing between the package and the chip, especially, and the rest of the system. And the PCBs don't have to be as rigid as what you saw on the previous slide. They can be quite flexible. So there's also flex PCBs, so-called, which allow for a single axis or flexible electrical connection in case you want to have that functionality. This is sometimes useful when you need to change levels or provide some sort of flexibility within your package. And those can support up to 4 layers of copper traces and can also be RF compatible. So in terms of what is the demarcation between the DC and RF, if you ask two people, they'll have three different answers. Where does that threshold occur? Typically for us, what we observe most commonly is that below 1 gigahertz, we treat essentially the package as DC. Above 1 gigahertz, we treat it as RF, and because the losses in electrical transmission become much more significant, and inter-symbol interference especially becomes a problem. So above this frequency, we essentially start treating the electrical connection as an RF, and therefore we modify the geometry of the conduction lines in order to solve that problem. And as for the components in the PIC that require the RF, those are typically lasers. They're sometimes modulated directly using RF signals. Then there are also modulators and also photodetectors, especially if they're operating at high speeds that require those sorts of speeds in order to reproduce the signal correctly. And you can see on this chip already that there is a significant difference between the RF lines and the DC pads. Those are quite easy to spot and quite easy to recognize. I won't be speaking exactly how to perform your RF simulations because this really depends on the chip you have, on the system you have. This is a very, very broad topic that could to discuss in its entirety could take several hours itself. However, because we're dealing with packaging, typically what we're interested is the interfaces. So if we desire interposers, that's when the packaging and the RF simulation comes into packaging. For example, what I'm showing here is a RF interposer that we're designing that has two layers which are crossed using a via. So this simulation is actually to set up to minimize the reflections and maximize transmission through this system. And RF simulations are necessary because you need to match the impedance. If you don't match the impedance, then it behaves like a refractive index jump, and you'll get strong reflections in your transmission spectrum, and you'll also start to lose signal. An example of such a simulation results are presented here on this graph, where in the red you have, let's say, the transmission in dBs, the losses as you incur as the frequency of electrical signal increases. And in black, you see the reflections. There are some specific frequencies at which your reflections are minimized. So in order to impedance match your entire system, you have to you have to tune the geometry of your transmission lines, the signal line, and also the grounding lines, and the geometries, the sizes of all the landing pads, because those things matter when you do those simulations. But as I mentioned, those are very specific to the specific chip that you have and specific system that you have. So I don't want to spend too much time. The RF materials are also, selection of RF materials is also quite important because what you're looking for are materials that have high electric constant or high relative permittivity, because then you can contain your electrical signal much better, so you can have a smaller pitch between your transmission lines. And also what you're looking for is a low loss tangent, which is essentially a dissipation factor, and it tells you how much of the signal are you using over the length of your transmission line. So this is I made this graph which shows several different classes of materials which can be used as RF. So FR4, which is standard PCB material, you can see has quite a high loss tangent and low permittivity. Rogers material is about an order of magnitude better than FR4, which is why it's used instead when you have a high-speed signals that you need to propagate. Then you have the class of ceramics, which, for example, low-temperature coal-fired ceramic, aluminum nitride, or alumina, they seem to have quite low loss tangent and higher permittivity. Then you have your semiconductors, which have even higher relative permittivity. I'll speak about glass a little bit later. So essentially, this is the selection of materials. And if you break it down, essentially on the left side of the graph, you have materials which cost less. However, you might have problems making them small, or you actually low loss. On the right side of the graph, you have materials which are going to be more costly, but you'll get a better performance out of them. So there's not only a question of low loss and high constant, but also how much are you willing to pay for your materials. So as I mentioned in the first webinar last week, what we're dealing with in packaging are typically the interfaces when we need to connect the photonic chip to the rest of the environment. And it so happens that when we need to connect the chip electrically, for example, to a PCB, we very quickly find out that PICs and PCBs are limited by their bond pad size. On the PCB, you have a certain limit of the minimum bond pad, while on the photonic integrated circuit, those bond pads can be made much closer. So what we do is most commonly is to have some sort of a pitch reducing interposer, such as one that you can see in this model over here, where we have a PCB interface which has both DC and RF lines, and those are pitch reduced onto the PIC to match that interface. And thanks to this, the PICs can be made smaller, of course, at the cost of having to make an interposer. So this specific PCB was made of ceramic, just single layer ceramic, which meant that it wasn't very costly. However, it wasn't cheap. And using interposers, of course, means that additional manufacturing packaging steps are necessary. So they have to be there. They have to be really justified in their use. Instead of ceramics, for example, you can use silicon interposers. Here's one example where we had a PIC which required 348 DC connections, so there's no RF here involved at all, which was good. However, you can see the relative size of the PCB that requires several quite large connectors, and then there are those bundled at the edge of this little interface. And then the signals are transferred over using wire bonding onto this silicon interposer, which is still significant size. This is not a small PCB. This is several centimeters across. And then the PIC is actually the smallest bit in this package. So this silicon interposers are quite good if you require quite fine line width, because they can be fabricated using lithography. And of course, silicon itself is very good for RF. However, as mentioned, they're very expensive, and you're paying a heavy price for the real estate. And this specific interposer, we can see it has like a gray sheen, which means it's finished in aluminum. However, you can also get those in gold, which makes them much more expensive. But as I'll mention later, they're much better for wire bonding or any sort of flip chip bonding processing. Then there's glass, which is a relatively new material that's used in interposers. However, it already captured notice of many big companies. For example, this is a picture from a notice from Intel that occurred a year or a year and a half ago, where they said they're going to be moving their production of substrates directly to glass, because glass is a relatively cheap material, but it also, as you can see from this picture, it allows for panel scale processing. So you can integrate your electrical components directly onto these little glass chiplets, and have them, after all the integration steps are completed, you can dice them out. You can also have in glass, you can design DC and RF tracks. Here is a screenshot from the glass interposer we designed here in Tyndall. You can see there are some DC landing pads, and also you can recognize some vias in between. For example, over here, there's a via. Since glass is optically transparent up to about 3.4 microns, you can also have in the future design those interposers not only to support electrical connections, but also optical interconnects. So it can serve dual purpose. Glass, however, has a very low thermal transmission coefficient, so it offers very good thermal isolation, which is both a good thing and a bad thing depending on the way you look at it, and I'll discuss that in the second part of the webinar, where we go to the thermal management part. Just a note, continuing on the scale of the thing, so you can see the bond pads on the PIC are typically when they're made, for example, for wire bonding or any processing, they're actually much, much larger than the actual elements that they're supposed to serve. So for example, here we have a ring resonator with an attached photodetector as a drop line, and you can see the bond pads are actually an order of magnitude larger than those. So there are things that you have to be careful when you're laying out your pick in order to have sufficient space for the landing pads when you're, for example, wire bonding. Onto the techniques of integration themselves. Of course, the oldest one is the wire bonding itself. So here's how the typical wire bonder looks like. You have a heated, oh, sorry. Sorry, my PowerPoint crashed, I believe. Okay. My apologies. Let me reshare it again. Okay, looks like we're back online. Again, my apologies for that. So here's how a typical wire bonder looks like. We have a heated device stage, which is used to
screen. Just diminish it for a second and close that window. Feedback to Microsoft.
Okay, it's not full screen. I see.
All that, and now make a big screen.
Right. Okay. So, I'll come back to this. So here we have a heated device stage, which is used sometimes to heat up the device right above the room temperature. But the most critical part of the wire bonder is a ferrule through which you feed the wire. And there's a spark initiator here that I'll show how it works on the next slide. But essentially, this entire setup is used to draw wire bonds between your photonic device and your interposer or PCB. And this method is reliable, and you can create with this, you can create long distance, quite long DC connections, even of the order of several millimeters. However, the wire bonding, as you see in this machine, this is a manual machine, so it's a quite slow method, requires several hours to connect to several hundred wire bonds, but it can be automated if you have a template that you can actually program your wire bonder with. So here is quite an old video of how the wire bonding process looks like. So first, a spark is by the spark initiator is forming a ball. Then it's bonded using ultrasound onto the bond pad on one side of the connection. Then it is drawn out by the movement of this ferrule onto the other bond pad, and again bonded using ultrasound to the other one. Upon which the tool is quickly withdrawn, and you saw the spark initiator coming very close to form another ball to be ready for the next connection. There are two types of wire bonds, depending on which speeds are you serving. So for DC, typically you have a circular cross-section wire bonds. They're typically 25 microns diameter, but you can have them perhaps larger. And they can be centimeters in length, even longer. However, this is not really recommended because you don't want to create very long wire bonds because they can cross and short circuit your system. Then the RF wire bonds are typically performed using ribbons, which have a cross-section which is non-circular. It's rectangular. For example, a common cross-section is 50 by 12 microns. And here you can see on this image, you can see those ribbons. And they should be as short as possible. You don't want to have very long wire bonds because then your losses increase tremendously. Then the next method is to solder the photonic chip and the interposer or your PCB together, and this is done using standard solders. However, what you can do, which is very useful, is you can solder ball jet your solder balls onto the bond pads. Here is you can see in the video how the process looks like. So the solder ball is shot out using compressed air through a nozzle, and then laser is heating up the solder ball as it passes through the nozzle above the reflow temperature, so that the solder ball melts, and in the molten state it makes contact with the with your surface and sticks to that surface if everything is made properly. So with this you can create hundreds of connections quite quickly, and those connections can be then made very close to the on-pick device. So you don't have to draw very long bond pads or RF lines. Your distance between the bond pads is actually quite close, of the order of the size of the solder balls. And these can be, typically they're 50 microns, but they can be, I think they can be made larger. A little bit of a side note on the bond pad finish, because depending on the foundry that you get your chips from, you can have your electrical bond pads made either in gold or aluminum, and those have impact on how which techniques can you use and how easily can you utilize them. Because you can't use standard solders directly on the aluminum bond pads. However, wire bonding works okay, as wire bonding is done using ultrasound. So essentially with aluminum, what happens is you create a very thin layer of oxide that you have to break through. That's why if you, for example, try to shoot a solder ball at an aluminum bond pad, it's just going to bounce off the oxide and not stick. That's why gold bond pads are preferable, and they're very good for packaging and solder adhesion, but gold is CMOS poison in silicon fabs. Then another types of bond pads you can have are either copper pillar bumps, which are created in the fab during the device processing. And this is how you can kind of mitigate some of the issues that I mentioned on the previous slide, because those are structures that are integrated directly into the PIC. And then you can deposit solder between those copper pillars, as you can see on the image over here, and then bond them together using reflow. So they're small size, and they're scalable in their foundry process. However, if you don't have access to those structures, then what you can do is kind of a workshop method, where you can apply a gold stud bump directly onto your bond pad using wire bonder machine. This is a workaround method, because it's not scalable, and your sizes of your stud bumps are going to be quite significant. So it's useful only for prototyping, but in those cases you can use that. So here what you can see is the interposer. This is aluminum nitride interposer onto which we deposited gold stud bump using a wire bonder. Then on top of that, we can deposit the solder ball and attach it using reflow to a photonic device. And speaking of reflow, typically what you'll be using when you're reflowing are either a reflow oven or a flip chip bonder. This is an example of the one that we have down in our lab, where the central part is a hot plate which heats up your circuit to a specific temperature. And over here also there is a beam splitter, which allows you to position your photonic integrated circuit, in this case of this example, relative to the interposer on the hot plate using some set of alignment markers. So once you align them using the beam splitter, then you can place them together and begin your reflow process. And reflow temperature depends on the material that you use. So typically, what you'll be using is thin silver copper, which is the SAC-205 eutectic, which has liquidus around 217 degrees centigrade. However, the typical reflow curve is the one that I'm showing over here in the top left corner. So typically, reflow temperature reaches 260 degrees. There are other eutectics that you can use for solder reflow, for example, gold tin, which has higher reflow temperature, but it can bond to aluminum bond pads with a little bit of surface processing. Then there's bismuth tin silver, which has a much lower reflow temperature, and again, this one will not bond to aluminum bond pads. And this table is quite important when you're looking, for example, to have a multi-stack device. When you, for example, have when you attach your electric integrated circuit to a photonic integrated circuit, I'll show an example of that later, using reflow, and then you want to take that subassembly and attach it again to your interposer, then in order to stop them from disassembling, we need to use two different eutectics. For example, you would use a tin silver copper to attach your EIC to your pick, and then attach that subassembly to your interposer using a lower temperature solder. So for these, you'll need to have different reflow temperatures. After your reflow is completed and your bond is correct, is established, electrical bond is established, what typically we want to do is to underfill the entire subassembly, because you're relying only on the connections between, that are formed using a solder, and the contact surface area might not be enough, and those could be, for example, detached quite easily, so you want to underfill them. This is typically done automatically. This is a very well-established process. It mechanically strengthens this bond. Of course, those underfills have to be electrically not conductive. However, they do provide a modicum of thermal conductivity of the order of 1 to 2 watts per meter Kelvin. Then what you can also do, there's a different technique that you can utilize if you have the same bond pad material on both sides of your link. When, for example, you have gold to gold, you can use thermocompression bonding. And what happens is you apply heat and force to bring them together, and through diffusion, essentially they compress to have a very uniform bond. Then the force with heat are interchangeable. So if you don't want to heat it too much, you can apply more force, and vice versa. So this is a quite interesting solderless technique, which provides a very good electrical contact. However, again, for gold, there are very little issues for thermocompression bonding. But if you want to use aluminum or copper, then you need to break the oxide and use neutral atmosphere, so that the oxide doesn't form between them. And the temperatures are significantly higher, as you can see here. For aluminum, it will have to be about 400 degrees, and for copper, about 380 degrees to break through the oxide layer. Coming finally to the types of electronic integration, I spoke a little bit briefly about this before. So what we started off several years ago is essentially NO-D electronic integration, where everything is in the same plane. You have here a pick in the center, then you have interposers to the side, which translate your bond pad pitch from the Rogers PCB to the pick. And then you have your PCBs on the sides with your DC connections and RF connections. So there is, in terms of integration, there is very little, to speak about. It's quite easy to design and manufacture, and also thermal control of this is quite easy, because you can put a tech and the heat spreader right underneath. So it's useful for prototyping. However, your RF traces are quite long. So, for example, if you have control in this case has to be somewhere outside. So the RF signal has to travel through this connector, through the interposer, down to the pick. So the traces are very long, and therefore you incur significant losses on that transmission. And of course, because this is most useful for prototyping, it might not be very well scalable. Then the improvement for that is a 3D technique, where you integrate, for example, your electronic controller directly onto the photonic integrated circuit, as seen in this picture. So with this, you have a very short RF tracks, if there are any, because your controller to the pick distance is very small. Packaging is also straightforward. You can solder reflow them one on top of the other. And it's generally a useful all-around solution, and it's quite scalable. However, the thermal control is quite challenging, because electronics is the major source of heat, and photonics is quite adverse to heat, as I'll speak about in the second section. But it kind of limits system integration, because you're kind of limited to the surface size of the pick and the number of electronic circuits that you could integrate directly on top of it. So you're paying for real estate in that case. The alternative, which is gathering much more steam recently, is a 2.5D integration, or something that will be soon called co-packaging, where you have your photonic integrated circuit and your TIAs or controllers reflowed directly onto the interposer, and the interposer is essentially your link between your pick and your EICs. And with this, you can have quite short RF tracks. I think I should go back to laser pointer here. Yeah. So here the distance between your pick and your TIAs is quite short. which again reduces the loss that you incur. Packaging is also straightforward. In the case of what you see on this picture, this was assembled in a single step. So all those elements were positioned on top of the interposer. This interposer is made of silicon, by the way. And then they were reflowed in an oven at a single stage, and then that interposer was again reflowed at a lower temperature onto the PCB. So packaging is relatively straightforward, and it allows for very high system integration and is also scalable. And it's now being used in a chiplet model where you might imagine this is an interposer that electrically and thermally interconnects your various photonic circuits and electronic circuits. However, firmware control of such a system is quite challenging. So the chiplet model I spoke about is essentially a new paradigm that people are working on to disaggregate the various functionalities among different nodes. And for photonics packaging, we arrive at such a co-packaged model, for example, where we have a central controller onto a PCB or a substrate, and each of the photonic integrated circuits are essentially chiplets which are attached to this PCB or a substrate. I want to also show some highlights of the work that we did here in Tyndall, for example, in terms of high-density co-packaged electronic interposers. So this is one that we did for one of the EU projects we're working on. This is a ceramic interposer that we designed, which has 20 electrical layers, which has to support 3,300 transmission lines. So just the design phase of this project was quite long. I would be surprised if it took less than 2 years, because all of those lines had to be checked for crosstalk between one another. And with this ceramic interposer, we could go down to 40 micron line width and spacing. However, even with that, such a small pitch, the total size of this interposer was quite significant. Here you can see by the scale, it's 10 centimeters by 7 centimeters. So ceramic is quite expensive material, especially when you integrate 20 layers into it. So we were paying quite hefty price for this. However, from this you can see that in order to make this system work, to have this interposer properly integrate the photonic circuit and some electronic circuits with the environment, there had to be an iterative, a very long co-design between various different layers, and that required a significant computational power. So this is not an easy thing to do. Then that device was integrated, as you can see, onto the PCB and assembled using standard optical packaging techniques that I'll be speaking about next week. However, the effort necessary to bring this into existence was quite significant. And as photonic packages become more complicated in the future, then you can imagine, and this is not going to be some easy thing to do and require a lot of iterative co-design. So the takeaway message just from the electronic perspective is that essentially, to recap, electric integration is, from the packaging perspective, is about delivering power to the PIC and communication between the chip and the environment or some other electronic ICs that are co-integrated with it. And with packaging, we can profit from many decades of research into microelectronics packaging. So things like wire bonding, solderable bonding, and reflow. Those are technologies that were not developed for photonics packaging specifically. They were taken from the microelectronics world, so we can profit from them. And then if you have RF signals, depending on where do you put your thumb on where RF starts, you will require specialized materials and RF lines and design considerations to have them working properly. And as we go forward in time, higher levels of integration are going to be quite more important. Therefore, the co-design of the electronic, thermal, and photonic layers will become much more challenging. And co-patching is becoming an essential method of actually manufacturing those devices. And a little bit of perhaps a side note right now, but you have to be careful when you're designing your system that any solders, underfills, or any other electronic layers do not contaminate your optical facets. Otherwise, you won't be able to optically connect to your chip. This seems like simple. However, you need to keep a specific distance so that you can actually attach your fibers afterwards. So now on to the second part, which is kind of related, the thermal management. So the sources of heat in the package are numerous. So typically those are the electronic circuits which are integrated. Lasers are also quite significant source of heat. Any heaters on the PIC that are used to modulate the signal are also sources of heat. Then there are DC connections and RF connections, especially they can be quite they can get quite hot. Then the heat-sensitive components on the PIC are typically lasers. If you have a laser integrated, then any change in temperature can vary the wavelength and power emitted by the laser. So you have to stabilize it quite carefully. And then there are some components on the PIC itself, which are quite temperature sensitive. For example, ring resonators, which are themselves controlled by thermal processes. So you have to be careful with thermal management. Unlike electronics, which can work comfortably up to 80 degrees and perhaps above without any significant drop in performance, in photonics you have to really take care of your heat management. Otherwise, you'll be in trouble. So here is a short video. If I can make it running. Sorry. Play video. Oh, okay, the video unfortunately will not play, but oh yeah, all right, now it'll play. Okay, so perfect. So you can see in this video what we're observing is the heat generated by the laser, and actually light is being absorbed by a ball lens that's sitting in front of it. And there's also a prism which directs the light. And you can also see that the DC tracks that are supplying the power laser are also heating up. So this little module is a significant source of heat. And if this is integrated into your package, then this is like a shining ball that you need to control. Typically, historically, what was happening, people would just place a tech and a heat spreader underneath and consider a job done. However, this led to some issues down the line, and therefore the conclusion that we arrived at several years ago that thermal management is quite underappreciated part of package design. But as we go forward with the high levels of integration of your lasers, modulators, PICs, and everything into a smaller footprints, thermal management and design have to be actually quite active in the co-design of the entire package. Thermoelectric coolers, I guess many people know how they work, so I won't spend much time on it. Essentially, you are driving a current through a set of connected legs, which are using Peltier effect to drive the heat from one side of your cooler onto the other side. So one side gets hotter and the other side gets warmer as you drive current through this device. Of course, if you reverse the either the polarity of your current or you reverse the tech, then you'll get you get hot side on the top. But sometimes you don't want to do that. However, there is a limit to how much of a temperature gradient you can generate using, or a cooling power that you can sustain using those Peltier coolers. So in case you require delta T of greater than, for example, 70 degrees, then you have to go for multi-stage techs. This is an example of 4-stage tech that can go, can get L delta T up to 130 degrees. However, there's a fundamental limit to how much you can extract heat because as you drive current through this device, you also have internal Joule heating. So at some point, you essentially are saturating the performance of the device, and you cannot cool down anymore. So there's there's a limit to how much heat you can extract using any particular cooler. So you have to select those quite carefully to suit your heat budget. Then next thing you have to take care during design effort is look at your thermal stack. So for example, on the non-integrated situation, such as this, where you have a PIC that sits in a heat spreader and your EICs or other controllers are far away on the PCB, then of course you'll have a low thermal crosstalk because FR4 has a quite low thermal conductivity of just quarter of watts per meter Kelvin. So there will be very low thermal crosstalk. However, you suffer higher electrical losses for it. On the other hand, if you have a 3D integration, as I mentioned, of your electronic circuit directly on the PIC, then you have very low electrical losses, but you suffer very high thermal crosstalk because silicon is quite a good thermal conductor, and the heat has nowhere to escape through except through the PIC. Then in the case of 2.5D integration, where you have everything integrated in the common interposer and it sits on a heat spreader, Then you have low electrical losses. However, crosstalk is quite significant, especially if the interposer is made of materials such as silicon. So again, you have to really look into how your temperature interactions between your EICs and PICs will affect your system. Then another thing that's worth considering is, are you thermally shorting your device? For example, if your submount, your metal submount, which also serves as, in this case, a heat sink to the thermoelectric cooler, is it thermally shorting your device? So if the heat is extracted from your PIC, however, it can go back up using, for example, these metallized sides. Typically, the way we deal with that is we just thermally isolate them using some plastic spacers. But this is sometimes overlooked, and then this can limit again the performance of your cooling mechanism. If you want to obviously control your temperature, you need some sort of thermistors, which are essentially resistors, which are very sensitive to temperatures. And typically in packaging, we deal with two types. One is a chip type, which is quite a small chip. The scale doesn't pay it justice, but this can be quite a small module of the order of like several hundred microns. And it can be integrated either directly onto a heat spreader. You can see here a very small bead. That's actually the thermistor. Or you can position your thermistor pads quite close to your PIC to register the temperature quite accurately. Then there's the bead type, which is non-compact version, but it's useful when integration with PCB is not possible. It's very difficult. However, you can get quite close to your PIC because you can integrate it, for example, as in this case, into the heat spreader itself. So your bead essentially sits just below your PIC. However, as mentioned, you need the thermistor to stabilize the temperature. There are also some other solutions that you can have when you want to improve your heat spreading capabilities. So PCBs, as I mentioned, are quite the thermal conductivity is quite low, but you can improve that, for example, by integration of a copper submount underneath the PIC. And then again, on the back side, you can integrate an aluminum heat spreader, which is connected to the submount. So you have very, very good heat transmission between your photonic integrated circuit and your thermal control stack. Going back to the 2.5D integration, if you, for example, have a silicon interposer, as mentioned, there can be quite a high thermal coupling between your EICs and your photonic integrated circuit, which is why silicon is, while quite a good interposer material in terms of electrical properties, it's not ideal. Of course, next to the price, it's not ideal as for the design of the thermal stack. That's another reason why some companies have been turning towards glass as their interposer material, because it has very low thermal conductivity, which means if you have your photonic chip and electronic chip integrated side by side, then you'll have low horizontal thermal crosstalk. And if you make these lines very short, then you can also have low loss RF transmission. However, these chips will still generate heat. So if you want to extract the heat from the stack, then you can integrate through glass vias, which will actually not only serve as your connection layer between the PCB and your chips, but also can be used to extract heat from your electronic circuits. So the thermal management in this case can be solved using vias, and this is actually quite a good engineering approach that we're actively working on in several projects. And the way you typically fabricate those vias in glass is you modify your glass substrate partially using a laser. Then wet etching kind of exposes the cavities. Then you put a PVD seed layer, and then you electroplate the rest of the cavity to fill them with, for example, gold or copper. And then, of course, you have to grind down to expose the bottom surface. So here is how it looks like from the side. And the effect of TGVs is essentially you are improving your vertical thermal conductivity. So if an untreated glass has 1.2 watts per meter Kelvin, in this case, for example, when we integrated a a thermal reference pick onto a glass substrate, you can see temperatures can reach up to 173 degrees. Then again, if we have integrated through glass vias, but they're unfilled with copper, then our thermal conductivity, of course, drops, which leads to higher temperatures. However, once those TGVs are filled with copper, then our vertical thermal conductivity improves quite substantially and the temperatures drop. So this is a very good method to actually thermally control you can even locally control your thermal, components such as picks. And we're using this method in several projects. This is just one example of which, where we integrate a laser and a photonic integrated circuit onto a glass platform. You can see here there are some through glass vias which translate electrical tracks from the top layer to the bottom layer. And again, the same is done for laser. There are some wire bonding pads for the laser on the side, but the heat extraction in this case will be done using through glass vias. And this ensures that due to very low lateral thermal conductivity, we'll have very small crosstalk between the laser and the pick itself. And thanks to the filled copper glass vias, we can have high vertical conductivity, which will extract the heat from the laser, so that so that it can work at a normal stable temperature. So takeaway message from the thermal part is you shouldn't underestimate thermal aspect of packages. They're actually quite critically important, and going forward will be even much more important as you want to, obviously, a thing that I haven't talked about, but is actually quite important, is your overall budget, because overall electrical budget, like your electricity bill, essentially, the more power you put into your package, you not only have to to drive it, but you also have to extract heat from it. So the power bill for just the heat management can be quite significant. That's why many data centers are now being built at the bottom of the lakes in order to help with that heat management. So don't overlook it; it's actually quite important. Essentially, the thermal management is an active area of research, and using glass and microtechs, these are areas that are quite active. We are quite active, and this is one that we believe this is a good engineering way. This is a good engineering approach to thermally manage your packages coming in the future. So thank you very much for attention, and if there are any questions, we'll take them now.
Very good. Thanks very much, Camille.